Hussain. I'm the co-founder and CEO of Marine Dynamics. It's an Australian space technology startup company aiming to develop engineering solutions for human habitation on Mars. The word Marine comes from Arabic and Urdu, which simply means Mars. So today I'm going to talk about um, our Craterhab technology, which is a patented modular large-scale habitation concept for Mars. It's proudly an Australian-made concept. Um, oh, sorry, how do I go to the next slide? Ah. So let's talk about some general comparison between Earth and Mars. So Mars is pretty small in all aspects as compared to Earth. It's 1/10 in mass as compared to Earth and 1/8 in volume. The surface gravity is merely 38% and atmospheric pressure is less than 1% as compared to Earth. So the main challenges on Mars in terms of developing a human habitation on Mars is first of all the distance. It's anywhere from 55 million kilometers to 400 million kilometers from Earth, depending upon the relative positions of Earth and Mars around the Sun. Low atmospheric pressure, and that's the key. That's the main key thing that determines what type of habitation engineering will be required on Mars because of the less than 1% atmospheric pressure. Um, Temperature on Mars is very low. It ranges anywhere from minus 150 degrees Celsius on poles at night to barely touching 10 or 20 degrees at equator, but mostly it hovers around minus 50 to minus 60 degrees Celsius. Then there's problem of radiation. So because Mars doesn't have a magnetosphere and it also has very thin atmosphere, so it cannot stop the ultraviolet and solar wind from sun. The level of radiation on Mars is roughly 2.5 times higher than what is experienced on the astronauts by the astronauts on the International Space Station. And of course, there's lack of resources and infrastructure, so everything you have to take from Earth until we find viable mining and manufacturing solution on Mars. So, in current technology, there's 7 months transit time expected for humans to get to Mars, and after a transfer window of that opens up every 26 months. Um, so there are other challenges that will dictate the type of habitation engineering that will be done on Mars. One of it is the size of the internal volume. So once you intend to settle humans permanently on Mars, you need a huge habitation volume that comes with their own challenges. Then you need an ease of construction, so it should be easier to construct on Mars than it can be on Earth. So anything that looks difficult to construct on Earth should be even more difficult to construct on Mars. So you need the simplest of the engineering solutions, and that should be done within the available technology, and it should be cost effective, and should offer the least material to volume ratio, because what we want to achieve is the large habitat volume with the least amount of material that we are going to use. And then of course topographical considerations, because Martian soil is less compact than Earth, so the engineering solutions should cater for that as well. So Craterhab is our patented technology. Is covered by 2 patents by the United States Patent and Trademark Office. One is for the design patent of the habitat structure, and the other one is how it functions or what's the deeper structure. That's a utility patent. So Craterhab Technology, it's a multi-purpose architectural engineering solution for large-scale human habitation on Mars. The basic unit of it is multi-layered composite fabric dome built over small Martian craters anywhere from 50 to 500 meters in diameter. And they would be anchored in the relatively more compact crater rims. So the Martian soil is loose because of the low gravity, but the crater rims are relatively more compact because they were formed as a result of the meteorite impact. And these crater habs would be interconnected through underground and surface tunnel systems. So the main objectives, what we are trying to achieve with Craterhab technology is to create micro-terraformed environments for long-term human habitation, so that humans can enjoy as close to Earth-like environment as possible, and Craterhab, the volume would offer that. And the habitation structure should be able to withstand at least one bar of internal pressure, which is equivalent to the Earth's atmospheric pressure, and the large internal volume, and it should, and we offer large internal volume habitats for multi-purpose use, and also to eliminate the need for frequent spacesuit egress, so that all the needs or most of the needs of humans living on Mars in the long term would be met inside the environment of the Craterhab, which are interconnected through each other. So the only reason to go out in the outer environment should be for exploration, mining, and external maintenance and repair. And they will also, because of the large volume, that will also offer safety against rapid accidental depressurization. In case of any depressurization event, a large volume would offer several minutes of reaction time so that you can take your emergency measures. Then it should also offer safety against radiation, because we are talking about surface structures. So there should be something in the material of the habitat that protects against the radiation. So we should talk about in subsequent slides. And it should be easy to construct from local and imported resources. So, so part of the Craterhab material would be constructed from the materials on Mars, and part of it would be imported from Earth. And it should be easy to repair, so that you don't have to undo the whole structure. You should be able to repair it easily, which we're going to talk about. And it offers, the Craterhab design offers least material to volume ratio, which reduces the construction cost and time. So why we chose craters is because craters are nearly circular shapes, so requires minimum engineering, and circular shape follows many engineering designs. Crater rings are relatively more compact than the surrounding ground, as we discussed earlier. And the crater offers a naturally excavated volume because it was formed by the meteorite impact. So craters are naturally excavated to provide extra volume of for same amount of material as for the level ground. So if you build a habitat on the level ground, a crater would give you nearly twice the volume with the same amount of material. And there are plenty of craters on Mars of all sizes, and the sloped interior of the crater is perfect for constructing horizontal underground access, which is easier than drilling vertically. So let's talk about the structural dynamics and parameters. Now, you might have seen many concept ideas of large-scale human habitation. Some of them include pillars, and I don't know why, because the main consideration for a construction on Mars is not to withhold the weight of the structure, but to withhold the inflation pressure, because the whole structure filled with 1 atmospheric pressure is trying to blow itself apart. So you don't need pillars. So that's not a viable idea. Then many of the habitat concepts demonstrate or show large glass domes. Now, the glass domes are practical on small scale, but on large scale, because they are filled with 1 atmospheric pressure, and outside atmospheric pressure is less than 1%. So any amount of wind, I mean, there's very little atmospheric pressure on Mars, but winds can still be fairly strong in case of a dust storm, and that can cause ripple effect in the glass, and that can risk shattering. On Earth, it doesn't happen because the pressures are equal, but on Mars, any slight change in the shape of the structure will cause huge stresses. So that's also not a viable idea. So what Craterhab offers is a flexible, multi-layered composite fabric dome, not standing on a pillar, but anchored through cables to the surface. So this is relatively more viable idea for large-scale human habitation concept. So if you look into the deeper structure of the Craterhab, so it consists of a hexagonal lattice framework of a triple layer of Dyneema. Now, Dyneema is one of the strongest synthetic fabric that can be manufactured on industrial scale. And through that lattice framework, there will be parallel Dyneema cables, which will be wrapped around by silicon composite bilayer of hexagonal patches. So this is from the drawings from our patent document. Sorry, just going back one slide. While Dyneema is more resistant to vacuum, silicon isn't. So we need to cover the silicon patch with a transparent vacuum coating, such as Kapton or polyimide, which is also practical. It's pretty cheap, actually. Now, periphery, the Craterhab would be anchored into the crater rim through a sandwich concrete wall, a triple layer sandwich concrete wall with two trenches. Through one of the trench, the Craterhab material will continue through into a soft torus anchor, which will then continue through uh, tether system to subterranean concrete radicular concrete anchors. The outer trench contains the accessory peripheral segment for backup Craterhab construction. So when this one material, one crater, one dome ages up, you can start constructing the outer dome without disrupting the internal environment. So once the outer dome is completed, you can take down the inner dome. And similarly, once the outer dome ages up after many years, you can construct the inner dome, and once it is completed, you can take down the outer dome. So this is to avoid any disruption into in the internal life of the Craterhab, and this is what we have done as a smart design and ease of construction to achieve the ease of construction. To further secure the whole structure will be anchored to the ground. In addition to the peripheral anchoring, it will be anchored by a biradial internal cable system to prevent the lateral movement of the dome as a result of Martian dust storms. This is just a cross section of the Craterhab. You can see that this is anchored through the sandwich peripheral walls and the central biradial cable system, and connected through the underground subterranean and surface tunnel systems. Now let's talk about the dynamics of the structure. That what sort of forces would be applied on the structure, because we are talking about huge domes of roughly 300 meters diameter filled with atmospheric pressure, so it's a lot of hoop stress. The hoop stress is what any cylindrical or any container containing high pressure, the walls of that container face. So the main reinforcing structure would be the central cables inside the hexagonal lattice framework, which will be parallel. Actually, there will be like a rings of dyneema, which will be parallel to each other and anchored and secured to each other. These will be the main stress, the main strengthening structures. So if we calculate the hoop stress, so if we consider that each Craterhab is capable of withholding at least 0.6 bar of pressure, so we calculated for a safety factor of 2.5, so that they should be able to withstand or contain up to 1.5 bar pressure. The tensile strength of dyneema is 3,500 megapascals. So we can calculate the hoop stress for a 5 centimeter thick structure of the dome. That turns out to be huge, actually, 450 megapascal. And if you multiply it by the total surface area of the dome, for example, if it's a hemi-ellipsoid with a diameter of 300 meters, the total surface area of the dome is 85,660 square meters. So the total hoop stress on the dome itself is 38,522 billion newtons. That's huge. So let's see if dyneema is capable of withholding such a pressure. So let's calculate the length, the total length of the dyneema cables. That turns out to be, if you're talking about hexagons of 10-meter sides, the total length comes as 19,740 meters. So the total surface area of the cables required would be 11,000 square meters. Now imagine if it's a single cable of 19,740 meters, the total surface area of 11,000 meters, so the circumference of the cable comes as 0.557 meters with the diameter of 177 millimeters. So that's not impractical. I mean, 177 meters is fairly something that you can think of, that yes, it can be achieved. So yes, so this is the thickness of the diameter of the dyneema cable system that would be required to withhold the amount of hoop stress. But what about the inflation pressure? Because Craterhab is not a circular or a spherical, it's not a spherical object, so it is anchored to the ground. So there would be an inflation pressure which will be trying to blow up the whole structure off the ground. So we should be able to calculate the number of anchors consisting of dyneema cables. So the total for the same size dome, 300 meters diameter, with a safety factor of withholding 0.6 bar pressure with a safety factor of 2.5, the total The inflation pressure comes as 12,840 meganewtons, and we're calculating with the strength of the dynamo. The total thickness of the dynamo cable anchors required would be 3.67 meters square, divided by the actual area of each cable of 177 millimeters, which is equal to 0.0246 square meters. So in total we will be requiring 150 cables anchoring it to the ground. So again, that's not impractical because this cable will be spaced around 6.3 meters from each other. So this is what will be required to withhold the whole structure. Now, what about radiation? You don't want to be living in a structure that cannot protect against the radiation, because that's where the surface underground habitation concept comes in. But we are living on the surface, so we need to find something to protect us against radiation. So we have developed this active integrated radiation shield concept, or AIRS, which is again covered through our patent. So what it is it's an active on-demand powered radiation shield. It creates non-ionizing magnetic field by utilizing the DC current through parallel cables inside the skeletal frame of the Craterhab, and it should be able to divert the solar charged particles away from the Craterhabs. Now, how much power do we require? Seems like it needs a lot of power. So this is the diagram from our patent. So if we calculate the amount of power, so what we need to do is we need to set some targets. So if we set a target that it should be able to generate an equivalent to Earth's magnetic field at 10 meters from the Craterhab. So the Earth's magnetic field is 5 into 10 to the power minus 5 Tesla. So this is the amount of magnetic field strength it should be able to achieve at, say, 10 meters from its surface. And if we have a copper wire going through the cables, so by using the Ampere's law, we should be able to calculate it. So we calculated it as each cable should be carrying 2500 amperes of current to achieve that amount of electromagnetic radiation, or the magnetic field, sorry. And the voltage that we required for copper cable based on its resistance is 36 volt. And if we are talking 36 volts, power required would be 90 kilowatt for each cable. And if you're talking about 20 cables lying in parallel to each other, that gives us a power requirement of 1.8 megawatt to create this radiation shield. Now, it may not be as good as Earth's magnetic field, because Earth's magnetic field is spread over thousands of kilometers. But this may still be good enough. I mean, any sort of protection, on-demand protection is good enough. So now the Craterhab, the utility of the Craterhab. So imagine that there's a cluster of small craters that we have created a population of, say, 3,000. So it consists of craters of different sizes. So one crater can be formed for residential purposes, like a few craters. There could be craters for manufacturing and might contain warehouses. There would be farming and agriculture in separate Craterhabs. There would be infrastructure for transport, sports, you name it. Each Craterhab can be used for any purpose that may be required. So the advantages that we see in a Craterhab technology over contemporary designs is that Craterhab technology offers large-scale modular solution, providing huge habitat volumes and the least material to volume ratio. And it gives a smart use of small craters on Mars, and providing easy access to subsurface facilities. It is cost effective, it's easy to construct, and with the ease of repair and replacement, and also protects against radiation. Now this is a short, low budget animation of our technology. I don't know if the speakers are working for the laptop, but we can try. Okay. presentation can be downloaded from this QR code as well. So that's the end of my presentation. Thank you.
Thank you.